The H2 plus ion is an exactly solvable system, and so it provides us with a good model that we can use to build our understanding of bonding and other types of systems. But we haven't really looked at the exact solution, and I want to spend a couple of minutes now just talking a little bit about what that looks like. All right, first of all, we have a wave function for H2 plus that is going to be written in terms of different coordinates, and I'm going to label them Xi, eta, and phi, as these are three Greek letters. All right, now what exactly are these coordinates? Well, if we were to draw our molecule, we're going to typically take the z-axis to be the internuclear axis. So our two atoms, A and B, are going to be separated by some distance r that will hold constant under the Bohr-Oppenheimer approximation. And then there will be an electron in something like H2 plus that's separated from these two nuclei by r sub A and r sub B. All right, so that's how we typically have set this up. We haven't said anything about the angular part, though. What we've done is mostly focus on what the radial part of this solution looks like, and we're going to need to include an angle, and in this particular set of coordinates, phi represents an angle of rotation about the z-axis, so it's an azimuthal angle. All right, now when we write this wave function and we solve it exactly for this coordinate system for H2 plus, it turns out that we can separate this into a part that depends on Xi and eta and a part that depends on the azimuthal angle theta. Now this isn't too different from what we saw with spherical polar coordinates. Remember, in that case we had three coordinates, and I'll draw them this way. Unfortunately, my z is vertical here instead of horizontal, but you'll recall that we had a polar angle theta and we had an azimuthal angle phi. And so phi basically is serving the same function in this sphere. These are called prolate spherical coordinates. So I should write that down. And phi is serving the same purpose in these coordinates as it did in the spherical polar coordinates, as an angle of rotation about the z-axis. Now it turns out that the form of this wave function is actually exactly the same as we found for spherical harmonics. So you may recall in spherical harmonics, we basically had a part that was dependent upon theta and a part that was dependent upon phi. And the part on phi looked like e to the I m phi, where m was an integer. It turns out the same is true for the H2 plus ion in this molecular case, where now our phi, and I'm going to use a different color to emphasize it, now our phi is going to be written as e to the I lambda phi. And again, lambda is equal to 0 plus or minus 1 and so forth. So just like m, it has those same values. Now, I'm only mentioning this because this is the part of this solutions that we're really going to care about. It turns out that the format or the functional form of the Xi and eta parts of this wave function are not impossible, but they're a little complicated, and it makes doing the math a little bit more difficult. So we're not really going to use the exact wave functions for H2 plus when we start talking about other molecules. Instead, we're going to move toward a system where we're going to strictly use linear combinations of atomic orbitals to construct our molecular orbitals. But the one part, as I mentioned, that we're going to care about is this part, because it tells us something about the quality of those functions, when we look at rotation about the internuclear axis. What could it possibly tell us? Well, remember that when we varied the quantum number m in the spherical harmonics, that could change the number of nodes, for example, that we saw about that z-axis. And the same is true of lambda. And in fact, for lambda, this is the only source of angular nodes. And we find that when lambda is equal to 0, we call that a sigma molecular orbital. In the same way that when m was equal to, or when the number of angular nodes in a hydrogen atom wave function was 0, we would call that an s orbital. So sigma, if you will, is kind of like the s of the Greek alphabet. When lambda is equal to 1, We call this a pi molecular orbital, which is kind of like p in the hydrogen atom case. When it's equal to 2, we call it a delta molecular orbital, which is kind of like d in that case, and so forth. We will keep going higher. I'll say typically these are the only ones one needs to worry about, and primarily we really only need to worry about these two. Okay, so let's see a little bit about what this means for these wave functions. Now, when we worked up our solution for the hydrogen plus ion, H2 plus, we looked at it in I'll say, radial coordinates. So we had, for example, wave functions that we added together to make plus or minus contributions. And we typically we're using the 1s orbitals as our means for creating these molecular orbitals. Now these are approximate, they're not like the exact solutions, but as it turns out we can mix any number of these together in creating a linear variational scheme for calculating the actual wave function, so we can get these arbitrarily accurate. But let's see what this means in terms of a three-dimensional picture for these orbitals. Now if I were to draw this just using the radial parts, we've seen what that looks like already. It looks something like this. Okay, where we have a wave function that comes up, and then it goes down, and then down like that. So this would be sort of what the bonding version of this wave function might look like. All right, but what this corresponds to in a three-dimensional space would be a spherical s orbital on this atom and a spherical s orbital on this atom, and they're going to work together to form a distribution of electrons that fill a three-dimensional space that looks more or less like an oblong ellipse. All right, so if I were to try to give this shading to make it look like a three-dimensional object, that's sort of what it would look like. So this is our prototype for a sigma orbital that represents bonding. Now we can also have a sigma orbital that represents anti-bonding. So I probably should just leave the plus sign here because I'll go ahead and write it again over here for the anti-bonding orbital. 1sa minus 1sb. All right, so in this case, we're going to have, again, two orbitals that are going to be more or less spherical, but now they're subtracted from one another. So we already saw that when we graphed this sort of as a radial case, we came up on the positive end here, but this side was negative because it was a minus sign, and to connect these two, we ended up going through here, and there was a node. And this is going to be characteristic of all of the anti-bonding orbitals that we'll see in this case. What this would look like three-dimensionally would be a pair of lobes that are separated and have a nodal plane separating the two of them. So what we'll do in general is we'll color the two lobes differently. So for example, I may color this lobe with purple, and I'll color the other lobe with red. Those aren't very distinct, are they? Well, I'll use different hashings. So these are up to the right and these are up to the left. Okay, but these would represent lobes of a wave function that have different signs. So, you know, sort of like this. This is the plus end and that's the minus end. So this would be the red and this would be the purple. All right, so our anti-bonding orbital is going to look something like this, where there's no probability of finding the electron directly in between the nuclei. So I want to specify that here, and this would be the bonding combination, where there most certainly is a probability of finding the electron in between the nuclei. All right, now when we begin to talk about these orbitals, we're going to talk about them in using labels that are relative to LCAOs, that is to say, to talk about the atomic orbitals that they come from. So in the case of the bonding orbital, we might label this as follows. This bonding orbital would be a sigma bonding orbital that arises from a combination of 1s atomic orbitals. So this is our bonding combination. All right, and the anti-bonding combination, how do we distinguish this? Well, what we typically do is we add a star to indicate an antibonding case. And again, it's coming from 1s orbitals, but the star means antibonding. All right, this is commonly used. You've probably seen it already in many instances in chemistry, but this is just to say we're going to follow that convention also. Now, we'll also introduce a different way of labeling these orbitals in another video, but this is how you'll see it labeled in many cases. So, for example, we might collect these together. So this is just telling us we are creating a sigma molecular bonding orbital out of 1s atomic orbitals. So it is an LCAO MO description of these things. Now, do we need to use 1s? We can actually use other orbitals to do this also. So for example, I might create a sigma bonding orbital out of 2s orbitals, in which case our two orbitals would look something like this. Continuing with the A and B labels just to separate our distinction of the two atoms that are involved. The antibonding combination similarly would look like this, and I'm going to put a star there. It would look like 2sa minus 2sb. All right, it turns out we can do this also with p orbitals, but we have to be careful about which p orbital we use. If we use the pz orbital, remember the pz is aligned along the z-axis, so I've got a lobe up here and a lobe down here. And if I were to take two of these together, aligned along the z-axis, so let's draw what that looks like. So here's our z-axis. Now I'm drawing it horizontally, and I've got one atom here with its p orbital aligned along the z-axis, and another atom here with its orbital lined along the z-axis. Now, if I were to add these together, I would need the two lobes in the center here to be the same sign. So when I add my coloring, okay, again, my purples are up and to the left, up and to the right, so I'll have these two representing the same coloring, while the two on the outside would be colored with the red in the opposite direction. So when these get added together, when the two nuclei come close enough together, what this will look like is something like this. We've got two nuclei here. They will have a lobe that looks more or less the same as the lobe that we get from the 1s orbitals, and then we'll have two outer lobes here that have the opposite sign. So the outer lobes are going to be the reds, and the two inner lobes have combined in an additive fashion to make this. All right, now why am I taking the trouble to draw this? What I want you to notice is that as we rotate around the z-axis using this angle phi, I don't encounter any nodes. There are no angular nodes here. In other words, so lambda is equal to 0 in the case of combining these two p orbitals. So as I write this as sigma 2pz, it's going to be 2pz on the A plus 2pz on the B added together to get this bonding combination for the two pz orbitals. Similarly, we would have one that would be a minus sign, and it would add a node here in the middle. That's where it would be. So we would end up having four lobes moved across here. We would have continue to have the nodes here as part of the p functions that gave rise to this molecular orbital, but we would also have a node in the middle indicating anti-bonding when we take the subtraction combination. Now there's one other that I want to introduce, and that is we talked but not really said much about the fact of an orbital that has lambda equal to 1. So this means that there's going to be a node as we rotate around the z-axis. There's going to be a node in this azimuthal direction. All right, so what that corresponds to is a nodal plane somewhere. So the way we might represent that is if I have two orbitals that are either px or py. So here they are. And this node that we have described is a plane that cuts these p orbitals in half. All right, so that's where this azimuthal node is for phi. All right, now we know the p orbitals have different sign lobes. So they'll have, say, positive lobes up here, negative lobes down here. And when we add them together, if we were to combine these two to form a bonding orbital, because the wave function have the same sign above and below this plane, and let me draw the plane again here too. We would have the following. We would have our bonding corresponding to this and this. But you'll notice that we still have a node in the azimuthal direction. We can only get lambda equal 1 if we start with a wave function that has a node along the z-axis, or I should say in rotation about the z-axis. So only if we have a node, an azimuthal node to begin with, can we get one when we combine these together like this. All right, so this is what forms the basis of a pi bonding orbital. And I think it's worthwhile to show, so this would be, for example, and I'll call this 2px. This would basically be an additive combination of the 2pxa orbital and the 2pxb orbital to get this. All right, we can also have an antibonding combination, and so let's see what that looks like. If I were to take the subtractive addition, so antibonding combination, and draw that, I'll have the following. Okay, and again, I want to be sure to label the z-axis as the internuclear axis. It turns out we will end up with an antibonding node here in the middle, so we'll have one lobe that comes out like this, and other lobes that come out like this and like this. So in other words, we end up with 4 lobes out of this, and they'll alternate in terms of the sign of the wave function. So, for example, we might have the purple lobes out over here and the red lobes above and below here. But the key here is that we still have this nodal plane that cuts the wave function in half, that comes from it comes originally from the p orbitals, but it is the thing that gives this molecular orbital its identity. Because when we have a node in this, when we have lambda equal to 1, that is always going to define a pi orbital of one kind or another. And this particular pi orbital is a pi star antibonding orbital. Okay, we'll look at these a little bit more in some different ways in other videos, but I wanted to get you grounded in how we actually use the solutions of the H2+ to talk about the molecular orbitals for larger and more complex molecules.